start off with a quick introduction to myself, and then we'll dive into sort of a 25-minute presentation. And then I've got a session for sort of discussion at the end, and we can keep it open as we go forwards from there. I'm new to running my own Zoom massive session, so if anything pops up and I don't realize, just cut me off so we can talk about it partway through. So we'll go roughly along with that. So welcome to the session. Session is going to be about Niobium anodes, fast charging tech from mine to Megawatt. And I'll take you through the journey from the problem through to hopefully the solution. Starting off with zooming out a little bit. So thinking in general, what is the problem that we're facing? Hopefully not a surprise to everyone joining the battery forum, where transportation of people, goods, raw materials, basically moving things around accounts for a huge amount of energy consumption around the world. Obviously powered a lot by fuel and more by electrified means these days, along with the associated impacts that we see. Zooming in a little bit more to applications which maybe some are familiar with, but maybe some are less so, is the more heavy-duty industrial use case kinds of battery technologies. These are kinds of things which are not necessarily electrified today. And you can go out and buy an electric car today. You can go out and buy, certain electrified devices, but it's a bit rarer to have, fully electrified ferries, for example, large applications that require a lot of battery if you want to run on a single charge. You've got applications such as trains and rolling stock, where you either have overhead electrified lines, you power it through diesel, and there are some small examples of hybrid, but there's no sort of full uptake of moving to electrified means. Here, buses and commercial vehicles, where we look for things like opportunity charging. So currently people more focus on having a single large battery that they charge periodically, which is a large upfront cost. So moving to smaller batteries you can fast charge is an ideal solution. Some energy storage, not every, but some energy storage where you have limited space, you want things to last without maintenance. There's a big need there. There's some more exciting things on the right. Always fun. We have motorsports, space applications, really pushing the limits of what you want from battery technologies. But what I will focus on today is more mining. So these big, heavy industrial use case mining vehicles that we have here. And all of these have in common that they need high safety, fast charging, so 5 minutes, 10 minutes for a full battery charge, not sort of limited SoC windows that you typically see for things like graphite-based systems, and long life. So really long, thousands and thousands, tens of thousands of cycles in some case for battery cells in order to operate, because a lot of these applications need uptime, and uptime means 24/7 in some cases, which leads to a lot of cycles for existing battery tech. So I'll take you through this as we continue on. For mining, in particular, you think of it as a whole industry. So we have, 30+%, about 20–30% global emissions from transportation. About 2 to 3% of global carbon emissions comes from mining alone, and that's from all aspects of it. If you think about the vehicles in use for these, really haul trucks, mining, going underground, overground, all the other light mining vehicles you have around and transportation account for a huge percentage of this. And it ranges quite a lot depending on how you've calculated it. This is more or less 69 million tons of CO2, 25 billion liters of diesel, 28,000 trucks. Not actually that many trucks, but they're all quite big along the way. This leads to very extreme conditions, but payloads of up to 240 tons that you need to move around, continuous use, 6,500 hours per year of operation, and a wide window of temperature that you need to operate in, from very low temperatures down to the high temperatures, along with dust, vibration, and you want safety alongside. These things really get pushed to the limits. They don't last very long, and diesel is the workhorse that most people use. Zooming in a little bit more, we have, if we think the ultra class mining trucks, these big ones that you see on the right, there's about 10,000 in operation today. And if we think of these conceptually, what do they need in terms of energy requirements, and what would a battery tech need to do? They require about 2,000 litres of diesel a day. So this accounts for a huge cost for a mining operator, $7.3 billion per year. If you think about electricity-wise, what does that represent? You know, it's quite a lot, really. It's 10 megawatt hours of electricity per day per truck. And if we took the classic approach of just put a battery on it, it's enough for enough operation to go back to a depot and recharge it. It simply doesn't work. You know, you can't have enough batteries on there without completely ruining the whole use case. 50 tons of batteries just to store enough electricity. So there do exist designs today looking more at sort of 1-2 megawatt hours of battery to try and get a fully electrified solution that you recharge multiple times a day. But these are still at the sort of prototypes demonstrator level here. It's early days. I've got some examples on the right of moving towards electrified solutions or overhead electrified lines like you might find more commonly in your head from the rail industry. So that's kind of the problem is, you know, we've got a lot of emissions, we've got a lot of requirement and desire here because it's basically equals cost for these mining operators, consuming huge amounts of fuel, and they don't really have a solution that's well suited yet in battery technology. So more specifically, what does it actually need and how could we get there? So instead of thinking about full electrification, because that presents a lot of challenges, we could think about hybridization as a sort of step between the two. So hybrid cells there need much smaller battery packs, and then we're talking about recovering energy and making the whole operation more efficient, so cutting the amount of fuel which these operations use to cut emissions and fuel consumption. And when we do this, there's a big balance between, you know, the C rate the battery needs to use, the size of this battery pack, and how long it has to last in order to have something that will have a financial incentive and actually prove itself, but also make an impact to those emissions. If we see on the left here, got a rough map of sort of a size of a hybridized battery pack, much more achievable than sort of 10 megawatt hours electricity that we showed before, 10 megawatt hour battery pack. We can go from sort of 50 to 225 kilowatt hours. And we can see how much energy can you recover from a regenerative braking, as an example here, in terms of how big the C rate needs to be in order for this to match up. And you can kind of see that if you can end up in the top right here, so very high C rates, very small pack, you have a cheaper overall solution. You don't have to have as much upfront cost in a large battery pack, and you can have high C rates to capture as much energy as you can to increase your fuel efficiency. That's what you sort of want from your battery solution in order to have more effective electrification. The number of cycles then goes hand in hand with this, because we can have battery technology that charges and discharges at 10C, 12.5C, you know, that's less than 5 minutes for a charge input power. Not very common in battery technology out there. The number of cycles then, if you have a small battery pack with a slow C rate, you know, this is unachievable with current battery technology. It's too high. So you want to have kind of a match of the right C rate, the right cycle life, the right battery pack in order to have a viable solution. So now I'll take you through battery tech, XNO, our niobium-based chemistry, and then come back to where we've gotten to with the mining application. Hopefully it all makes sense along the way. In terms of battery tech, I'm talking about lithium-ion batteries overall. There's a lot of things which you have to optimize. You know, all batteries have trade-offs. You'd never have a battery that ticks every box for every single thing, but the fundamentals of what's possible are always based in the battery materials that are in use, really. So what active materials you use, is it liquid, is it solid state, and so on. On the left, I highlight a few of the important parameters that you might have for a mining-based lithium-ion battery. Things like, instead of dollar per kilowatt hour, the important metric is actually dollar per kilowatt hour per cycle. What's the cost efficiency? How much money are you saving in this operation, rather than what the upfront cost is? You know, you need the wide temperature performance, you need cycle life, of course, high safety, and you need that power and energy density combined. If we look at standard lithium-ion battery technology that exists today, I've broadly categorized, tried to make it pretty simple, with NMC graphite, NMC being the cathode, LFP graphite, silicon-based anode chemistry, LTO-based anode chemistry, and sodium ion. And we can see, to try and hit these metrics of energy density, lifetime, and chargeability, NMC graphite, good at energy, silicon even better. But when it comes to the lifetime requirements of such high utilization applications, that they're simply not a good fit. They fall away too quickly. LFP graphite is then quite interesting and is in use for some of these trials. Has a decent lifetime, enough energy density, but its chargeability and operation at high temperature become a bit of a challenge. Lithium titanate is very attractive for lifetime and for fast chargeability, but has a limit on energy density and a high cost. Sodium ion is then sort of similar in this LFP graphite space, but of course there's a number of other challenges relating to it. So where does niobium come in? And what am I talking about? So as a battery as a whole, I've got a little schematic on the right here for those who are less aware. For lithium-ion batteries, we're operating with liquid lithium-ion, organic electrolytes. We have our anode materials, cathode materials sandwiched together. And what we've been working on at Echion is changing that fundamental anode active material away from your graphite, your silicon, LTO, to a niobium-based chemistry. And at Echion, we call this XNO, mixed niobium oxide. By changing it here, we managed to get around these fundamental limitations. You can't fast charge graphite because of lithium dendrite formation. You can't take it to low temperatures as well. LTO can indeed do this, but has limitations on energy density. And silicon, while it can fast charge and it can operate well, it doesn't last long enough for these kinds of applications. That's where we focused. We've got a drop-in solution here, so we just normal liquid lithium ion, normal battery manufacturing, and combine it with normal cathode materials along the way. So I'll take you through the fundamentals of roughly how the material works, and then we can go into a bit of cell performance and then back along to the link back to mining. So how does it work? So XNO, niobium based, these are based on the Wadsworth niobium oxide phases. So what this means is its crystal structure, the arrangement of the atoms in space. I've got a schematic down below to explain what these Wadsworth niobium oxide phases look like. We have structures here of niobium surrounded by oxygen atoms, and there will be other elements in there as well. And in order to get these structures, rather than a perfect octahedral matrix, as you have on my diagram on the left, these crystal structures are formed by having some shear effects taking place. You end up with oxygen sharing. And in a simple way, what this means is you end up with structures on the right. This is an example where it's not as perfect on the left, octahedral matrix. We have something that's more held in place by these shear structures of edges and corners where we have these oxygen sharing. And what this means is when we want to put lithium ions into it, it's an intercalation approach, lithium ions will flow very easily through these spaces which you can see between these octahedra without limitation. That some of the best-in-class lithium-ion diffusion comes from these materials, way above those of lithium titanate. It's a very constricted pathway coming through. It's also a very stable, reversible process because we have these shear edges locking everything in place. You can't expand and break apart the structure going through. And because of niobium chemistry itself, you can see in my diagram in the top right, this is half-cell performance of lithium titanate compared with graphite, compared with niobium XNO here. You can see the voltage is a lot higher, but a lot more capacity can be extracted because niobium has 2 redox from 5+ to 3+. Safety-wise, there's a fundamental safety here shared by LTO and XNO. The voltage is higher, which means that you don't have any risk of lithium dendrites when you try and fast charge. If you try and fast charge graphite, you have overpotentials leading to voltage dropping below 0, and you end up with this lithium dendrite formation, which is a real challenge to manage for fast charging. Those are the materials in general. It's very brief. I appreciate that. We can come back to it if you've got any questions on it. For XNO in particular, these materials are very interesting. They're a very diverse material class of space. Not all materials are made equal, though. We've done a study in the past with colleagues in Cambridge, looking at a whole bunch of different versions of these materials, different compositions. You can have hybrid ones with tungsten, with titanium, with almost any element in the periodic table to make them. But they have trade-offs. Some have more energy, some have more power, some have issues of Coulombic efficiency. And some are more expensive. You can make them out of very expensive materials. Gallium niobium oxide you can make. I'm not sure you would want to along the way, and manufacturing processes. So at Echion, what we focused on is really finding the right niobium chemistry, still based on the same principles, but on finding the one designed for the right balance of energy, efficiency, and power for these industrial use cases. Along our way, we haven't just focused on sort of material design optimization and providing it out. We've been working a lot on trying to link all the way from raw material to anode material through to cell design, all the way down the end in order to de-risk it, to get it into market as quickly as possible. And this means understanding degradation of lithium-ion batteries. Been a big topic for a long time with all battery chemistries, particularly so for us, because we focus on these more dollar per kilowatt hour per cycle. The more cycles we get, the more kilowatt hours we get, the more compelling the technology is for a wider scope of applications. And when we think degradation at a very high level, this approximates to really two effects. One is power fade, so increase in resistance in a cell, and one is energy fade, of decrease of capacity in the cell. And these come from many different sources, but at a high level, that would be loss of active material, cathode degradation, forming rock salts, for example, or dissolution, loss of lithium inventory, or film formation. Now, at Echion, we sort of focused a lot on doing this, and I got some examples. I won't go in much detail here of us looking at, say, bad examples. So cross-sectional results of a niobium-based electrode, showing an example where this hasn't performed very well, and we found that root cause, and now we've resolved it. And that's the sort of approach which we take at Echion, not just here's a good material, good luck, it's here is good material, here's a good chemistry, and we understand how it works, so we can make sure that it works in that industrial use case for as long as possible going along. So what about the cells themselves? How do they actually perform, and where are we in terms of commercialization? So for a typical NMC XNO lithium-ion cell performance, you'd imagine specs roughly along the left as I show here. Energy density is similar to that of LFP graphite, hovering around the sort of 300 watt-hour per liter range in terms of volumetric energy density and gravimetric, as you can see. And charge rates, depending on the trade-off you're looking for, either higher C rate or lower C rate, but always in that 5 to 10 C continuous and looking for higher pulses. Cycle life, as I said, essential. 10 to 20,000 cycles is what we're really looking for, the high safety and wide temperature range. This is roughly what we can achieve with NMC XNO chemistry, or are working towards with clients. And last year, we've had an announcement by one of our clients, the Clanchet, who makes cells for premium cells for applications such as marine, electrifying for exactly our kind of use cases, launching the first niobium-based cell out there in the market. In terms of cell performance specifics, I'll now go into showing you a bit of data to hopefully give you a bit more background and where it sits versus this LFP and NMC-based chemistries. So on the right, we have a plot which we've made here of different chemistries, including niobium. We carry out an accelerated aging test, selling 10,000 cycles. We do this at 1C. 1C rates takes multiple years to test, so we do things quicker and higher temperature to get these results as quickly as we can. And what we've done is we've tested some of the most recent CATL cells, EVE cells from China. So graphite NMC, graphite LFP at a 2C, 2C rate at 45 degrees. And you can see, obviously, the NMC is higher energy density, the LFP chemistry is lower, but both degrade at a similar rate under these temperature conditions. So it doesn't take long for them to degrade beyond the point of not being able to use them for these applications where we need these longer cycle life. LTO lasts for a very long time, but does have this limitation on energy density that you can actually hit. And what we show for the niobium chemistry here is two results. One results from our labs in Cambridge, where we work in small pouch cell prototypes modeled out here. And then a result from one of our clients working in 40 amp hour cells, showing that we can achieve that similar energy density that you can have for a graphite LFP chemistry. This is top of the range stuff coming from CATL, achieved already by some of our clients for these applications. So sitting in that sort of graphite LFP energy density, but the cycle life that you'd expect out of LTO with those other benefits as well. When we look for very high C-rate operations, we then look for more, if you think about a hybrid application, you want to have high input, high output, continuous, and it's being used all the time. Obviously, you look more at drive cycles, and you'd have quite different results there in a proper mining operation. A simple test is just doing symmetric 10C cycling. So 6-minute charge, 6-minute discharge. We cycle 80% of the SSE window by doing this, and you can see we're roughly out to 10,000 cycles in our cell design that we have here. So this is really the technology which we need to enable the mining industry and others similar like it, which you can't achieve with your LFP chemistry or NMC without having to limit it even more in energy density. So limit the SSE window more and more and more, such that you diminish the advantage that you have. Other effects worth mentioning is energy efficiency. It's a bit more nuanced, but the energy efficiency of our XNO chemistry is higher than that for an LTO chemistry, 90% versus 80%. What this means is we generate less heat by operating at higher C rates. So when you think about modules and packs and mining vehicles, you don't want to mitigate that heat if you can avoid it, because all batteries degrade faster at higher temperatures. And I've spoken through these other bits. So the XNO is providing that higher C rate, temperature stability, and long life that we need. I have another couple of examples of some other clients of ours for more room temperature operation. So looking at 25 degrees, 3C symmetric cycling, and you can see these cycle very stably without any real resistance growth from the system. And this resistance growth is an additional very important parameter because when we deal with high C rate applications, there's a square in there somewhere about current and resistance and heat. So you really want to avoid any resistance growth that you can get, because then you need to oversize your cooling system along the way. So now I'll move a bit more into niobium in general, and then go into the mining industry, and then I'll stop talking for some questions and discussion at the end. So what about niobium? I'm sure some people may know about it, some people may have never heard of it. Niobium itself, there's a nice picture of some niobium oxide in the top right. A white powder, non-toxic, air stable, a bit nicer to work with than some of these cathode materials, nickel and cobalt and so on. It's about as abundant as lead in the Earth's crust, but it's not as widely exploited so far. There are resources across the world. I've highlighted on a map sort of the viable resources that exist, predominantly produced in Brazil today and Canada secondarily, but there are active efforts to mine and exploit this in the US, Central Africa, and in Australia as well. Dominant use today is in steel. So there's plenty of appetite to grow this. There's plenty of resources around, and there's a lot of benefits for doing so. For the XNO supply chain itself, so this is about the niobium raw material, and we've obviously worked on making active anode materials from it. Now, we thought quite a lot about how we should go about doing this. We're based in the UK as our headquarters. We've got staff working for us in the US, we work in Asia, we work in Australia, and in Brazil. And because we supply globally, and a lot of niobium comes from Brazil, we decided to locate our first manufacturing facility in Brazil, co-located with the niobium mine and refinery. So we have a UK-based R&D and pilot plant, and we successfully scaled our operation and have commissioned and are selling from our 2,000-ton per year XNO facility, as you can see in this picture, in Brazil, which is opened end of 2024 with Brazilian niobium company, technology company CBMM, one of our shareholders and big partners in the niobium field. This is roughly equivalent to about 1 gigawatt hours worth of lithium-ion cells. Gives you an idea of the scale. It's not the size of the the cathode industry in 2030 will be like 10 million tons. We're well below this, but it's sufficient to supply into these initial mining industry and other applications, and big scope to increase the scale beyond this. We've also focused a lot on environmental impact, of course, because we're based in Europe, where we've got things like the European Battery Passport, of course, and we've most recently done a public environmental product disclosure, and this really showcases our reduced impact of the raw materials versus graphite versus LTO, a lot because of how the material is mined, refined, and processed versus lithium and versus titanium. So bringing it all the way back, we've gone all the way from raw materials of niobium, where that comes from, the XNO supply chain and plant, the cell chemistry. What about going through to mining? And here is where we are at the stage of a light mining vehicle out in operation in Australia. So as you can see on the screen, Switch Technologies company in Australia has been working with Echion and they've successfully made an electrified hybrid electric Toyota Landcruiser 79 series. You can see here, it's kind of a light mining vehicle workhorse. It's around the world. And we've installed it with a 24 kilowatt hour battery, which you can see here on the screen. And this has been out being demonstrated, and we're collecting a lot of performance data from it at the moment in Western Australia. We've got 2,000 signals being streamed from it, from the battery through the vehicle operation and beyond, all with the intention of showcasing the technology for light mining vehicles, but really for mining in general. You know, we need real life data, not just cell performance data, in order to work on these larger mining vehicles, which is where most interest lies. I've just got a bit of a section here on moving forwards to powering these big, large haul trucks. You can see down here in the bottom right, we've got an example of one, a Cat 785. Where burning 100% diesel is no longer that viable for mining. It's too expensive to continue doing so. There's huge interest around the world. There's a conference, trade show next week, the Electric Mine in Chile, which we'll be going to, exactly about this with all the large mining operators. But equally, 0% diesel is not so viable either. You know, full electrification of every operation is simply not going to work because of the reasons I described before, too large batteries. So hybridization is really the most capital efficient way to get these things going. And with XNO, we can provide that with a 10C input output power, find that ideal balance of battery pack size, energy, and have a short payback period for the operators in mining and lower the impact at the same time to really enable that electrified mine. So I'll more or less stop talking there. There is a video series on YouTube I highly recommend checking out to sort of take you through the process of hybridization for this. And then I'll open to questions there. I've got some other topics we can go through for a discussion if we wish, but maybe I'll go straight into questions to begin with. I can't quite see where you all are. One moment. There we go.
Hello, Alex.
Hi, Eric. Go for it.
What's the catch?
Good question. There's always a catch in battery technology. The catch here is that the energy density is not as high as for your NMC style systems. And
but we don't need that. Everybody in there is going for LFP, so obviously NMC isn't necessary. That's not a good comparison.
The other catch is that the upfront cost is higher than an LFP system. So it's about having that upfront cost is higher for a niobium-based chemistry, but the lifetime is significantly more. So it's not a perfect fit for every LFP style of application, but it is when you really need that lifetime. You don't want to go through the cost of replacing these LFP batteries over time.
You're just replacing the anode with niobium-based composite. And the anode is what percentage of the total cell cost, of the total pack cost?
For a percentage of the total cell cost, off the top of my head, something along the lines of sort of 20-ish%, 20 to 30. But yeah.
So in the worst case scenario, you're only increasing the cost of that 20% of the cell, right? So it shouldn't be a huge cost delta. What does LTO go for comparison? That's really your real comparable, isn't it?
Yeah, so LTO cells go on the market for quite a lot at the moment for the high performance modules and packs, but there are also cheaper options out there. So for these, you'd be looking more on the order of, in some cases, all the way up to beyond $1,000 per kilowatt hour, and some cases further down, but not down to the same levels that you would have of, you know, the $50 per kilowatt hour of LFP chemistry. But that's for cells. For modules and packs, it's more around that sort of level.
So if you've got an LTO pack, well, the incumbent, say Toshiba, is already in market, and we know what their price is. So they're pretty well monopoly on that chemistry. So their cost
For
structure is what
LTO at the moment.
but they're
Yeah.
already in the machines that you would like to get into. Perhaps you will provide an opportunity for LTO to come down in price through competition, but probably where we are now and where you will be, it's probably not going to be the same answer. If you've got Brazil, that should be a lower cost production just of the chemistry itself, but we're really only talking about 20% of the battery cell itself that you could be playing around with the price, right? So, and even LTO can be doped with niobium if they want some of the performance benefits without totally tossing the existing chemistry out. How are you going to compete with them on that?
So Toshiba are also commercializing a niobium-based chemistry as well. So they see the advantage of a pure niobium-based chemistry coming on the way. And there are people out there doing niobium and LTO mixtures, as you say. For us, it's more that a lot of these applications have tried LTO, but have not found it having enough energy density to even be competitive because they can't get the energy in the given volume or weight restrictions that they have. And so therefore the interest in the niobium chemistry is actually, in some cases, it's the enabler of the application itself in the first place.
Okay, you said at one of your first slides that you compared 2,000 liters of diesel to the equivalent, which would be 10 megawatt hour pack that you would have to put in. Do those trucks carry 2,000 liters of diesel for an entire day's work?
I don't believe so, no. They refuel as they go around, yeah.
Right. So comparing 2,000 liters of diesel to one size of one single battery probably doesn't cut it either. If you do two full refills of diesel, then that'd be 500, and then your battery pack would similarly, presuming that there's a charge cycle in there somewhere,
Yeah,
wouldn't
so
have to be the full size.
it's a very good point that you raise, and I think it goes back to let me flick over to that slide once more. It's 2,000 liters of diesel per day, but I'm not saying they carry all of this in one go, which is
Right.
about 10 megawatt hours of electricity. But if you wanted to have depot style charging as you would for classic electric vehicles as you do today, these are more sort of 1 to 2 megawatt hour battery sizes that people have been looking at where they recharge a few times per day. But that it results in an extremely expensive upfront cost in terms of sheer mass of battery and the amount of power and downtime that you need to recharge them based on existing tech. So it's about moving towards these even smaller battery packs that can charge a lot quicker along the route or make use of these regenerative braking techniques.
Right. Your comparison is always to a bad alternative, but LTO is actually a good alternative in most of the dimensions that you're could be competing with. So it's best to compare them to what the realistic alternative is. If you want to get into the ABB account, you're going to have to prove that, right? And they're already
Precisely, yes, we do hold ourselves versus LTO, indeed, quite a lot. Charles, sorry, I saw you put your hand up there.
Yeah, thank you. In terms of that demo vehicle for Switch, it says 24 kilowatt hour battery. What would be the approximate quantity of niobium in such a battery?
Not a great deal. I mean, 24 kilowatt hours is not that big a battery in terms of size.
no.
No, you can sort of see it. I don't have the number off the top of my head. But you can sort of get a feel for here, and that you've got the individual modules inside of these. You have an idea here for the number of pouch cells which are going in.
What are your current collectors?
But when you, sorry, go on.
So niobium and okay, let's look at a bigger battery. Let's just talk 1 megawatt hour. What would be the approximate amount of niobium in kgs?
Yeah, so when we do this approximation, it's typically the 2,000 tons per year takes you to a gigawatt hour worth of lithium ion cells is roughly the sort of scale.
So that's 2,000 tons of XNO material, which is not only niobium.
That's correct.
Oxide.
Yes. Yeah.
What's your mix?
So we have our own formulations where we've mixed it with other elements as well. It's not just pure niobium because you have some performance limitations. There are some other elements in there in order to get the performance which we're looking for.
Thank you. Thank you.
Yeah.
Are your elements sourced from the same sources geographically?
Geographically, yes. Yeah. Similar area.
Does the niobium dominate the cost of the other elements that you have in your mix?
Yes, in general. So the niobium as an element, as I say, it's less exploited so far today. It's the more expensive component out there. But as more people utilize it, more people are using it in the battery industry as a whole, we expect prices for it to come down substantially.
Well, the primary use case is currently in steel, you're saying. So the existing mining operations are feeding that use case or that demand case. And steel is hardly, they're quite familiar with commodities and materials. So I wonder how much of your demand for this and other suppliers would change in terms of volume of
Yeah,
mining.
it's a good question. So for the steel industry at the moment, so niobium is used, say, 80–90% of it is used for steel. The other applications, sort of high value alloys, or the oxide itself is used in optics and catalysts and things like this. For the steel industry, they use ferroniobium as an input material. And for other applications such as batteries, you would use the oxide as an input material. And at the moment, in terms of resources and use of the mining facilities, there's plenty of additional capacity there in order to increase the production that you need for, say, an extra 100,000 tons in existing mines without too much issue, to be honest.
So I work at Globe Metals and Mining, which is the mining company in Africa there, the small green part in Malawi,
This one,
at the bottom there. And we will produce in full capacity 3,000 tons of niobium oxide. So we are deciding to only produce niobium oxide, not ferroniobium.
Yes.
To cater for that.
So any other questions in the audience there?
Hey, Alex, I do have a question. So you guys looking at a hybridization strategy for some of the mining trucks, as they are more or less already has been hybridized for a couple of decades now, because they're essentially a diesel gensets and powering your electric motors and drive the wheels. So for a typical, let's say your ultra class mining truck, how much of battery do we need to fully hybridize it? Or is it going to be case by case based off your mining operation duty cycles?
I mean, in some cases it is case by case, but in the example which I've worked through here for these large category 785, 789 kind of vehicles, you have an idea of the ideal sizes of your battery pack from this discussion which I had here. It'll be in the order of, as you can see, the sort of 100 to 200 kilowatt hour size of pack is sufficient to hybridize and capture enough regenerative energy for a compelling case for these kinds of size of trucks for hybridization. Not to say that you can't fully electrify, I've just used this example for this particular mining size of vehicle.
And have you guys looked into the carbon dioxide emission reduction by simply hybridizing and recuperating energies? Because some of their mining sites, they are looking to carbon neutral by 2030 beyond. What is the benefits in that aspect of environmental impact?
Yeah, so we would expect an environmental gain, of course, but we haven't fully calculated it out yet. We're working on our life cycle analysis at the moment. So we've done a sort of cradle to gate based on all the work for making our materials, making cells, but we want to sort of collect a bit more operational information and data before we can sort of commit to what we would really expect. But we are intending to capture a huge amount of this energy and reduce fuel use. So from our light mining truck trials, we're hoping to extrapolate out initial ideas of what that will be like. Yeah.
Thanks, Alex. Thanks for the presentation.
Thanks.
Alex, are you able to use aluminum for both current collectors?
Yes, we are indeed. Yes, we can use either aluminium or copper, but obviously we use aluminium for cost in most cases.
Weight.
Yeah.
So if you're able to use aluminum, do you also have the same safety characteristics as LTO?
Yes, similar, or perhaps slightly better, but it really depends on how the cell has been put together. So we really need to be careful when you talk safety to comparing physical products identical to each other, but more or less the same as LTO, yes.
Right. So LTO, one of the sales points of that, of course, is the safety aspect, that they're even willing to put it in retail vehicles under this driver's seat, say, because it's not going to blow up the driver.
Yeah.
You didn't mention safety at all in your presentation. It's probably not the number one trigger for a mining vehicle. However, it's a useful point to point out that it's actually comparative to all of your other chemistries, relatively safe to work with.
Yes, absolutely. I mean, it's from the as I said, from the dendrite point of view, we have very high safety from this perspective, but also due to the higher voltage that we work at, or rather lower full cell voltage that we work at, we have increased safety as well. Yeah.
Are you be in Stuttgart?
Sorry?
Will you be in Stuttgart in a couple of days?
Not in a couple of days, but I'll be in Stuttgart for the AABC Europe coming up shortly.
Okay.
Perfect. Any other questions at all? Tyler, any questions?
From my side, no. I appreciate the questions from the group. Eric, you brought up something important on the safety side of things, and yes, it's definitely been really interesting. I come from the mining background, and yeah, safety is definitely top of mind for a lot of industries, and the ability to execute on a battery strategy that you're not having to firewall with crazy safety mechanisms has been a top of mind for a lot of companies. So really appreciate the question, and yeah, I'd love to connect with some of you on LinkedIn.
Excellent. If there's no more questions, I think we're almost up for time. So I might stop the session there. If there's anything else people want to ask, fire away. Otherwise, I'll give it a close there. And thank you very much for all your attention and discussion so far.
Thank you, Alex.
Thank you.
Thanks, guys. If I can figure out how to stop it, that's the other question.